this section, we will learn about the related rates, the word problems on the applications of differentiation and the derivatives. Find dx over dat when y is 3 and dy over dt is 5. So you're given an expression here, 4x cubed negative 5x square, 5y square equals negative 13. So let's differentiate this with respect to the variable t. So how do we know that we have to differentiate with respect to t? You see the denominator term and look out for the differentiating variable. So differentiate 4x cubed with respect to t. First you differentiate the exponent, which means it's a power rule of differentiation. So you have 4 times 3, which is 12x square. Now you have to differentiate this variable x again with respect to t. So in the previous sections, we have seen that when we did implicit differentiation with respect to x, we did not differentiate x. But now we have to because the variable is different. So differentiate the variable x with respect to t. So it is dx over dt. Then you have a negative sign. So bring that down. That's this negative sign here is coming down. Differentiate 5y square with respect to t. So first you want to differentiate the exponent to the power rule of differentiation. So it's 5 times 2y, which is 10 times y, 10y. And now you have to differentiate this variable y with respect to t. So it is dy over dt. Then you have a negative 13. Differentiation of any constant term is 0, so write 0. So you differentiated x with respect to t as well as y with respect to t. Now you're asked to find dx over dt when you're given some specific values. You're given y is 3. So wherever you see a y value, you're good to plug in it as 3. And the derivative of y with respect to t is 5. So this value here is given for you in the problem. It is 5. So dx over dt, this is the only unknown in the problem, but you also want to find x value before you proceed finding dx over dt. So let's see what is the possible value of x we can plug in and how do we find x here. So let's start with the equation 4x cubed negative 5y square equal to negative 13. We are given the value of y, which is 3. So I'm going to write this as 4x cubed. I'm plugging in the y value. So it's negative y and then I have a 3 square equal to negative 13. I'm going to simplify this. 3 square is 9. 9 times 5 is 45. So I'm going to write this as negative 45 equal to negative 13. I'm going to add a positive 45 on both the sides. So I get 32 on the right hand side. I'm going to divide by 4, so I have an 8. So this is actually a cubic term, so I'm going to write this as cube. But now x cube is 8, which means x is 2. I'm going to bring the 2 value here and then I will plug in for x square. So this becomes 2 square. So I have just one unknown in this equation, which is dx over dt, and I solve for it. So let me write 12 times 2 square times dx over dt negative 10 times 3 times 5 equal to 0. So 10 times 3 times 5, when you simplify, this is 30 times 5, which is 150. And 12 times 2 square, when you simplify, 12 times 4, which is 48. So you solve for dx over dt. You have 150 divided by 48, and this is your final answer. In the next example, you have at noon ship A leaves a port. At noon, ship A leaves the port traveling north at 35 km per hour, and ship B leaves the port, same port traveling east at 1 p.m. at 25 km per hour. Question is asking you what is the rate So that what is the distance, at what rate is the distance between them changing at 3 p.m.? So first let's draw a right triangle with XYZ as the length of the sides and mark ship A and ship B. Ship A leaves the port traveling north and ship B leaves the port traveling east. So also mark here that there is a 1 hour lead. This distance shows that there is a 1 hour lead for ship A. The question is asking you at what rate is the distance between them changing at 3 p.m. And all you know is time from 1 p.m. That's given for you. Okay, now you can write rate at which the variable x, which means the distance of ship A leaving the port, changing with respect to time t. This is given for us in the problem, which is 35 kilometers per hour. Similarly, you can read dy over dt, the rate at which the ship B leaves the port at 1 p.m. The rate will be 25 kilometers per hour. Then you want to see at 3 p.m. you want to find what rate is the distance between them changing, which means you want to say what is dz over dt. This is what you want to find. So you want the exact values for x and y here, which is not given in the problem, but just the rate of change of x and y is given. So let's try to find x and y. So use a Pythagoras theorem for this. And you can write x plus 35 square plus y square equal to z square. So now differentiate this 2 times x plus 35 times dx over dt. You're differentiating the inside function. Y square is 2y, differentiate y dy over dt. Z square is 2z, differentiate z dz over dt. So once you have differentiated, plug in x value So let me write that x value here on the right hand side. So at 3 p.m. we know that the distance y will be 50 kilometers and the distance x will be the double of 35, which is 70 kilometers. So you want to plug it in the expression of the Pythagoras theorem. So 70 plus 35 the square plus 50 the square equal to z square. Then you solve for z and you get z equal to 116.297 kilometers. Now that you have the z value with you, if you come back to this implicit differentiation expression, you should have just only one unknown, which is this dz over dt. This is the only unknown. So we have all the other variables. So let's start plugging in. We have 2 times 70 plus 35 times 35 plus 2 times 50 times 25, 2 times 116.297 times dz over dt. So simplify this expression for the derivative value. You have dz over dt equals 2 times 105 times 35 plus 2 times 50 times 25. Bring the coefficient in the denominator. 2 times 116.297. So with all this, we have this rate change for the distance between the two ships, 42.35 kilometer per hour. So the tricky part in this problem is applying the implicit differentiation correctly and also analyzing these x and y values from the given data. In the next example, a person 1.8 meters tall is walking away from a 5-meter high lamppost at a rate of 2 meters per second. At what rate is the end of the person's shadow moving away from the lamppost when the person is 6 meters from the lamppost? So let's draw here. Say here is the person. And the height of this person is 1.8 meters. Is away from a 5-meter lamppost. So let's make this as the lamppost and say this is 5 meters. Is walking away, the person is walking away from the lamppost at a rate of 2 meters per second. And what rate is the end changing? So let me mark this distance as x and say this distance is y. So this part will be x minus y. And the shadow will be this part of the problem. So I'm going to say the shadow. We'll be using the similar triangles concept to do this problem. So before that, let me list what we want to find in the problem. Question is asking you at what rate is the end of the person's shadow moving away from the lamppost when the person is 6 meters from the lamppost. So this distance is represented by x, the end of the shadow from the lamppost. So you want to find dx over dt. And the y is given for you when the person is 6 meters away from the lamppost. So this is y, it's given for you, y equal to 6. You're also given the rate at which the person is away from the lamppost. The person is moving, walking away from the lamppost, which is dy over dt. It's given for us in the problem, and this is 2 meters per second. So let's use the concept of similar triangles to do this problem. Say use similar triangles. Consider the ratio x minus y, which is the side of this smaller triangle, divided by 1.8, which is the height of the smaller triangle, equals the side, the base of the larger triangle, divided by height of the larger triangle, 5. So these are the base to the height ratios. This is for the smaller triangle and this is for the larger triangle. So let's try to simplify this expression. You can cross multiply these fractions. Write it as 5 times x minus y equals 1.8x. So 5x minus 5y is 1.8x. So 3.2x equal to 5y when you subtract 5 and 1.8. Now you're all set to differentiate this expression. So let's differentiate. 3.2 dx over dt equals 5 times dy over dt. Now you have 3.2 times dx dt. We are given the dy over dt ratio, which is 2. So dx over dt will be 5 times to 10 divided by 3.2. So this will be 3.125 meter per second. In the next example, a water tank has the shape of an inverted right circular cone of height altitude 12 feet and base of radius 6 feet. If the water is being pumped into the tank at a rate of 10 gallons per minute, 1.337 cubic feet per minute, approximate the rate at which the water level is rising when the water is 3 feet deep. So first let's draw an inverted right circular cone for this problem. Say the radius is r and the height is h. And this radius here is given for us, which is 6, and the height is also given, which is 12. So let's write the volume formula for the right circular cone, which is 1 over 3 pi r square h. And let's differentiate v with respect to t, dv over dt, the rate at which the volume changes, or like the water is being pumped into the tank. This is given for us, and it is 1.337 feet cube per minute. The question is asking you at what rate the water level is rising, which means you want to find dH over dt when that water is 3 feet deep. So when you know that height is 3 feet. So let's try to differentiate the given expression here, the volume expression. When you do the differentiation, you have dV over dt equals 2/3 pi r h dr over dt. We are doing the product rule. And then 1 over 3 pi r square times dH over dt. So if you plan to differentiate the given expression for volume with respect to t, all you have is this. Well, when it comes to plugging in the values, you will be able to plug in the values for dv over dt, and you have the value for the radius as well as the height. So all these are good. But dr over dt, the rate at which the radius is changing, this is not given to us, and we'll not be able to find this either. So without having any information of dr over dt, we will not be able to find dH over dt using this particular implicit differentiation expression. So I would say for this particular problem, differentiating the volume formula is not going to help. So we'll say that this is correct, but this will not help us to finish this problem. So let's think of a different method. Let's say we'll try the similar triangle methods like the previous example. So I'm going to say use similar triangle. So I'm going to consider this piece of the triangle from the cone. This is the radius, this is the height, this is 6, and this is 12. So using similar triangles, I'm going to consider the radius by height ratio, which is 6 over 12, which is 1/2. So all I have is r over h is 1/2. I can rewrite this as r equals 1/2 h when I cross multiply h on both the sides. Now that I have a value for r in terms of h, let me go back and plug in the radius formula into the volume expression. So volume 1 over 3 pi r square h now becomes 1 over 3 pi times r is h over 2, so h over 2 square times h. Simplify this a little bit, you get 1 over 12 pi h cube. Now that we have a nice expression for V volume in terms of the height h, you're good to differentiate this with respect to t. So dV over dt equals 312 pi h square. Differentiate h again, you have dH over dt. You know the volume for dV over dt, this is given. You know the value for height given. So you have only one unknown in this equation, which is dH over dt. Plug in h is 12 and plug in dV over dt is 1.337. Simplify, you have dH over dt equals 0.1891 feet per minute. So this is the rate at which the height changes. This example will be your practice problem. Before you look at the solution on the blackboard, I want you to try this. We'll move on to the next one. A revolving beacon in a lighthouse makes one revolution every 15 seconds. The beacon is 200 feet from the nearest point P on a straight shoreline. And find the rate at which the ray from the light moves along the shore at a point 400 feet from P. So let's draw a right triangle here. Angle is theta. See, this coordinate here is P and then this is X. This distance is 200 and then we have H. So here is the ray of light. So we are given the rate at which the angle changes. We know it's one revolution per 15 seconds. So we're going to write d theta over dt as 2 pi divided by 15. 2 pi is one revolution. And the measurement units will be radians per second. Then in the next step we have 4 revolutions being given every minute. So we want to rewrite the d theta over dt as 4 times 2 pi, but this is in minutes, so you're not seeing a denominator, and the units will be radians per minute. So now we want to find dx over dt when x is 400. So start with a Pythagorean triangle and try to bring down the ratio for the tangent angle. So from this triangle we can list the tangent of the angle theta is opposite by adjacent, so x over 200. Now differentiate this with respect to t. So you have differentiation of tangent, which is secant square d theta divided by dt equals 1 over 200 as a constant. Differentiate x with respect to t, you have dx over dt. Now you want to find dx over dt in the problem. So write dx over dt equals 200 times secant square theta d theta over dt. D theta over dt per minute value is given for us. This is the 2 pi expression. Oh, sorry, this is 8 pi. The value is given for us. Secant square theta, we have to calculate here to finish the problem. So let's do a calculation for secant square theta. We know that secant theta from the given right triangle is h over 200. Well, h can be written as the hypotenuse of the right triangle, x square plus 200 square of each side, and then sum them, sum of the squares of the triangle divided by 200. So you want to evaluate this expression at x equal to 400. So secant theta becomes 400 square plus 200 square divided by 200. Simplify and you have square root 200,000 divided by 200. So you square on both the sides to eliminate the square root, and you have secant square theta equal to 5. So bring the secant square theta here, value plug in 5. So simplify this expression. You have 25,132.74 feet per minute. And the next problem will be for your practice. The next one, two sides of a triangle have fixed length 3 feet and 7 feet, and the angle between these sides is decreasing at a rate of 0.05 radian per second. Find the rate at which the area of the triangle is changing when the angle between the fixed sides is 1 radian. So let's draw this. This is the height, perpendicular height, and say this side is 3 and then theta. And say this is length 7. So using this right triangle, you can write sine theta is hypotenuse opposite height divided by the hypotenuse 3. So you can write an expression for height h sine theta, 3 sine theta. Now list all the given quantities. D theta over dt is negative 0.05 radians per second. This is given for us, the rate at which the angle changes between the two sides. And then you're asked to find dA over dt, the rate at which the area changes when the angle theta is 1 radian. So you want to write area equals half times base times height. So it's half times 7 times height, base is 7. Then you want to write area equals 7 half. We know the expression for height, which is 3 sine theta. So you can write 7 times 3, 21 divided by 2 sine theta is the expression for area. So let's differentiate this. dA over dt equals 21 over 2, derivative of sine function is cosine, derivation of theta is d theta over dt. Now start plugging in the values. This will be 21 over 2 cosine of 1 radian, and the d theta over dt is negative 0.05. Simplifying all this, we get an answer of negative 0.2837 feet square per second. We'll end this section here.